Suppose there are 5 people with t-shirts and hats numbered as shown. If they exchange their hats such that no person has same number on hat and t-shirt, then it's called a derangement. So this is an example of a derangement. How many such derangements are there? So using the inclusion exclusion principle, you can write this answer as 5 factorial minus 4c1, which is 4 choose 1, 4 factorial plus 5c2 3 factorial, and so on. And after some algebra, this can be written as 5 factorial upon 0 factorial minus 5 factorial upon 1 factorial, and so on. But calculating this value is like very tedious, so we can try to find an alternative method. So the alternative method is a recursive relation. So let me just show you what recursive relation we are talking about. It's this thing. You might have seen this somewhere already. So all of this is just a proof of it. So A's hat could have gone to any of the other 4 people, and in return he could have got the hat of the same person or some other person. If it's the same person, then his hat went to, then we can just switch their hats and ignore them. So for example, if A's hat went to B and B's hat went to A, then you just switched their hats and then you ignore them, because now they received whatever hats they had to receive. So those hats are now not roaming in the air, they are on somebody's head, so you can ignore it. And now the question just boils down to these remaining 3 hats. So now it's just the hats 3 4 5 that are remaining, and they can't go to people with t-shirts 3 4 5 because it's a derangement, of course, right? But wait, if they can't go to 3 4 5 and there are just 3 hats roaming, then that in itself is also derangement. So it's a part of the bigger derangement d5, but it's also a smaller derangement itself, so it's d3. But then how many such cases can we get? We can get n minus 1 such cases, or 4 such cases in this case, because it's not just that A and B can be switched, it can also be A and C, A and D, and A and E. So that means d5 can be replaced by 4 times d3? No, because there's one thing that we didn't consider. So it's because it's not always the case that A receives B's hat. So as we saw in the first example, over here A is not receiving the person's hat to which its own hat went. So A's hat went to B. So here I have named this as 1 2 3 4 5, but you get it, it's supposed to be A B C D. So A's hat went to B, but then B's hat went to C, and E's hat went to A. So he didn't receive B's hat, and these cases are also valid derangements, so we need to consider those as well. So what are the rules for these different cases? So we already covered the case where you switch A and some other person. The other case is that you don't switch just A and some other person, you instead give A's hat to that other person, but you give A somebody else's hat, right? So if B receives A's hat but A receives someone else's hat and not B's hat, then we can only ignore B. So we can definitely ignore B because he received a hat. That hat is now not roaming anywhere, it's just on his head. You can ignore that guy. So we'll just consider these 4 people because they have hats roaming on their heads. Now let's give them some shoes with numbering as shown. So this is just for better understanding of what's going to happen next, but even if you ignore these shoes, it's okay, it's the same thing, right? So adding the shoes, it doesn't change the question because the shoes are basically irrelevant to the question, so it's still the same thing. So now what are the things that we can consider for this case? First of all, we already consider that that B's hat cannot go to A because that would be once again just switching, and we already considered that case, so we won't be considering that again. So we have the first rule that hat number 2 cannot go to A, which has shoes with number 2, and hat number 3 cannot go to person with shoes 3, of course, because it also has like t-shirt 3, they also have t-shirt 3. So that obviously cannot happen because it's a part of the derangement. So now once again just consider the hats 2, 3, 4 and 5. They cannot go to people with shoes 2, 3, 4 and 5. Wait, but that's just another derangement. So hat 2 cannot go to A because we already considered that case. Hat 3, 4, 5 can't go to C, D, E of course. So hats cannot go to people with same number on their shoes. That's a derangement. And number of such derangements is D4. But A's hat, the first hat that it actually had, that could have gone to any of B, C, D, E, and you could have ignored any of B, C, D, E, not just B. Why not C? So the actual ways for such cases to happen, that would be 4 times derangement of 4. So now we consider this factor into our equation as well. So we have d5 equal to 4d3 plus 4d4. So d5 is 5 minus 1 times d5 minus 1 plus d5 minus 2. So more generally, you can prove that this equation is true. So you can prove it either by induction or just doing this for n people instead of 5 people, doing the whole process once again. But the fact is that this is true for n generally. And yeah, that's the relation that we wanted to prove. And this is much easier to use than this equation where you just have to calculate stuff. So if you are a computer, then this equation is like a jackpot because you don't have to recursively keep on finding derangements. But if you are a human, you would want to find like multiple derangements so that you can have a system instead of just writing on the page continuously, writing all of these numbers, calculating. So that's why this formula is so useful. So, and of course, if you are already given the derangements, that you can find higher derangements with that. So yeah, I'll see you guys in the next video.